So let's go on and start to talk about semi-definite programming, which, as I mentioned, is a kind of generalization of linear programming, which is very useful for algorithms, especially for constraint satisfaction problems and other optimization problems. And to motivate this semi-definite programming, we're going to think about a very simple optimization problem, the max cut problem, which we've mentioned before already in this course. So the max cut problem is quite simple. In the max cut problem, you're given a graph, G, an undirected graph. And unlike min cut, you're trying to do the opposite. So you're trying to find a subset of vertices S, like these ones circled in yellow, so that S as a cut cuts as many edges as possible. So remember that an edge is said to be cut if it has one endpoint in the set S and one endpoint outside the set S. So in this particular example, almost all the edges are cut. This edge is cut. It goes from inside to outside. This edge is cut. This edge is cut. This edge is cut. And despite the picture, this last edge is not cut because its endpoints are both in S. Okay, so this cut 4 edges, and that's actually the maximum cut in this graph. It's impossible to partition the pentagon into 2 sets such that it cuts all the edges because the pentagon is not a bipartite graph. Okay, so max cut is given the graph, find the cut of largest cut size. And as you know, this is an NP-hard problem. And in particular, that means, unlike the min-cut problem, which we saw last time can be exactly solved efficiently using a linear programming relaxation, you kind of know that's not going to happen for max cut, because otherwise you'd be solving an NP-hard problem in polynomial time. Okay, so what that means is, if you try to do this paradigm of like writing down an integer linear program that captures maximum cut, relaxing it to a linear program, and hoping that's not such a bad relaxation, maybe solving this linear program, getting an optimal sort of fractional solution, and then rounding it to a true solution S, this paradigm we talked about last time, well, you're not going to get the situation that this always gives you the optimal maximum cut, because then, max cut would be in polynomial time. And in fact, this paradigm fails really badly for maximum cut. So it's a great strategy in general facing an optimization problem. Formulate an ILP, relax it to a linear program, but for max cut, doesn't work well at all. And if you try it, the only thing you'll really be able to prove about this strategy is that the size of the cut it achieves, whatever however your strategy works, the size of the cut it achieves, the number of edges from S to S complement, will be at least a 1/2 fraction of the optimum, which is okay, but we saw like a variety, there are a variety of really simple algorithms that can achieve the same approximation behavior. So you don't really need linear programming to get this kind of weak result. In fact, in the de-randomization lecture, we talked about how you could just pick a random partition and it would cut half of the edges, half of all the edges, which is certainly half at least the optimum max cut in polynomial time, and this was easily de-randomizable. Okay, so that's a shame that this powerful linear programming technique does not work, but it's going to be the reason we extend this version called semi-definite programming. And as a bit of a spoiler, using this tool of semi-definite programming, we'll actually be able to get a polynomial time algorithm that achieves a much better so-called approximation factor. It'll give you a polynomial time algorithm that returns a set S that always achieves at least 87% or 87.8% of the maximum cut, which is pretty great. And in fact, it's known that there's evidence that doing better than this 87.8% cannot be done in polynomial time. It's unique games hard, and we'll say what this means in a much later lecture of the course. Okay, so this is to psych you up for trying to develop a generalization of linear programming that will help us solve max cut. Okay, so even though I told you it's gonna fail, let's talk about this standard paradigm for max cut of trying to write down an integer linear program that exactly captures it and relaxing it to a linear program. Okay, so in an integer linear program, we usually introduce variables. We're going to introduce variables xv, one for each vertex. with the intent, they're supposed to be 0 or 1, and the intent is that xv should be 1 if vertex v is going to be in the set S, and 0 otherwise. Okay, so xv in the integer linear program is supposed to be the indicator set for a set S. But now we need to start talking about whether or not S cuts or doesn't cut various edges. And so after a few moments, or in fact inspired by the min-cut LP we talked about in the last lecture, you would be motivated to introduce variables y, so vw, for every pair of vertices vw that are supposed to be 0 or 1. And again, with the intent that y vw should be 1 when x, when thought of as a cut, actually cuts the edge vw. Or in other words, yvw should be 1 if and only if xv differs from xw. So that's going to be tricky to enforce with linear constraints, but let's just go on for now. What is the objective? Well, we're trying to maximize the number of cut edges. So if we could set all these variables up like so, the objective function would be to maximize the sum over all edges vw in the graph of y vw. That would exactly just count the number of edges cut by the set indicated by S. And that's a perfectly linear function. It's just the sum of some of the variables. Okay, but what we have to worry about is this constraint that we're trying to capture. I mean, of course we have to worry about the fact that this is an integer linear program, and like we cannot eventually insist that xv and yvw are just 0, 1. But like this is the standard worry that we've always talked about in this paradigm. We're of course going to relax these constraints to make an LP, or we're going to try, where we're going to let xv be a real number between 0 and 1, and yvw be a real number between 0 and 1. But even if we do this, we have this difficulty that it's not clear how you can enforce this constraint with linear inequalities. And it's quite funny, actually. If you think back to min-cuts, I know we didn't talk about it too much, but at the very end of last lecture, we did see a linear program that was capturing min-cuts. And in that linear program, you see, one way to try to express it is to say that yvw should be at least the absolute value of xv minus xw. Okay, and think about these variables as taking 0, 1 values. This sort of exactly works. You know, as long as xv and xw are different, this right-hand side is 1, and so you're obligated to make yvw 1. But if they're the same, you're allowed to make yvw 0. And for min-cut, you would, of course, always be trying to make these y's as small as you're allowed. Now, this, at first, does not look like a valid linear inequality for linear programs because it has these absolute value signs. But actually, it's fine because if you think about it, this inequation can be converted to two proper inequalities that capture it. You know, you have to just say that yvw is at least xv minus xw, and yvw is at least the negative of xv minus xw. So this is just shorthand for two inequalities that you really could include. On the other hand, for max cut, so in max cut, you're always trying to make the y's as big as you can. And you could enforce this if you could write down that like yvw is at most absolute value, because then again, that would say that if xv and xw get different 0, 1 values, you're allowed to set yvw to be 1. But on the other hand, if xv and xw are the same, then you're obligated to set yvw to be 0. But unfortunately, like this this inequality, you just can't write it as like this. You can't convert it to two like normal inequalities, right? If you just think about it, you know, this doesn't work. So that's the difficulty. So we're a little bit stumped at this point. Even if we're willing to go to an integer linear program, we're a little bit stumped as to how we can encapsulate this constraint. Any questions? There's a question. The question is it known whether we can express yvw equals the indicator that xv not equal to xw through a set of linear constraints, say by defining a few more variables? Short answer is no. You might say like, oh yeah, maybe I'll try to play around. I'll try to add a few more variables, and I'll exactly encapsulate this. I guess basically the answer is no. But you can still have a smart idea. The question is there a result that proves this is impossible? I guess it's like saying if you allow yourself to have an integer linear program, can you encapsulate this with inequalities? I guess I would say provably no. I don't want to try to prove it on the spot, but I would say provably no. Probably not without exponentially many inequalities. That's my guess, but don't quote me on that. My guess is not without exponentially many inequalities. But okay, there is going to be a smart idea though, and the smart idea came from circa 1990 in some paper of two people, Delorme and Poljak. And let me try to tell you about their smart idea. First thing, this is not essential to them, but to explain their smart idea, we're going to make a notation change. It's kind of my favorite notation change. Instead of using 0 and 1 for the xv's, we're going to use plus or minus 1. Okay, so now switch in your mind xv to be like plus or minus 1. And now also switch in your mind yvw should also be plus or minus 1, and you should it should try to be the product of xv times xw. Okay, and so there, notice that means that like yvw is supposed to be plus 1 if xv and xw are the same, because plus 1 times plus 1 is 1, and minus 1 times minus 1 is 1. And yvw should be negative 1 when xv and xw are different plus or minus 1 values. So again, it's just changing notation. This is going to be like the constraint that it's very hard to encapsulate, but I wanted to switch notation like that. And with this switch notation, the objective function is still fine. With this switch notation, you see this little expression here, a half minus a half times yvw. Remember, this yvw is 1 if xv and xw are the same. So when you plug 1 in here, you get a half minus a half, which is 0. So this expression is 0 if xv is the same as xw. And if xv is different from xw, then yvw is minus 1, so this expression is 1. So with this new notation, this parentheses expression is the indicator that xv differs from xw, and so this objective function, which is still a linear objective in the variables yvw, exactly encapsulates max cut. Okay, so what I'm trying to say here is, I've just switched notation. So far, this program, if you could carry it out, exactly captures max cut. Okay. So let me throw in a few more equations that are fine. Certainly, if you have this set up, then yvw should equal ywv. So I can throw that in. That's a linear inequality, or a linear equality, so that's fine for LPs. And again, if yvw is supposed to equal xv, xw, and xv's are supposed to be plus or minus 1, then yvv should always equal 1. And that's another linear equality, so there's no trouble in throwing that into an LP. And let me just pause again to say that, like, now, this program also captures max cut exactly. Okay, I no longer have to explicitly say xv and xw are plus or minus 1 valued, because, well, if you have that yvw equals xv, xw, and you also know that yvv is 1, then means xv squared is 1, which means xv is plus or minus 1. Okay, so still, this is not like a linear program or anything, but it still captures max cut exactly. And furthermore, this piece, without this tricky constraint, is a linear program. It's a linear objective, linear equalities, in fact. So that's good. Okay, so here's really the smart idea of Delorme and Poljak. It's going to say, let's take this LP, kind of forget about this equation, but instead imagine that we put this LP together with this weird constraint. And the constraint is, given the y's, just that there should exist some real numbers xv such that yvw equals xv, xw. Okay, so this is a weird constraint. But let me call this, for reasons we'll eventually see, the moment constraint. And I still want to say that this linear program LP, together with this moment constraint, exactly captures max cut. This moment constraint is some weird constraint. It's not a linear inequality constraint, but we're still at the point where these two things together exactly characterize max cut. Okay. So now I can finally say their idea. And their idea is to try to enforce moment using linear constraints, just on the YVWs. So the only variables are YVWs. And this moment constraint says there exist real numbers like x such that YVW equals XVXW for all V and W. And that's not a linear constraint, but like the idea is try to encapsulate it with some linear constraints. Now, we're not going to be able to succeed in doing this exactly, because if we could succeed in doing this exactly, then, well, the conjunction of everything would be a linear program, which we could solve in polynomial time, and then max cut this NP-hard problem would be in polynomial time. But just like with this sort of ILP to LP relaxation paradigm, we're going to kind of try to do a good job of encapsulating these moment constraints. So let me talk about this heuristically for a bit, and then I'll get talking about it properly later. Right. So this is the idea, to try to enforce these moment constraints using linear inequalities on the YVWs. Well, suppose we didn't try to enforce them at all, and we just took the LP constraints and we gave those to the ellipsoid algorithm. The ellipsoid algorithm can, solve linear programs. And I'm going to be a little bit slightly heuristic in the following discussion for a bit. We handed those the LP inequalities, actually they're equations, off to the ellipsoid algorithm without this moment constraint at all, and said, hey, ellipsoid, solve this for us. Okay, so ellipsoid would solve it. And maybe it would return some values like YVV. All the YVVs are 1. That's a constraint. It's got to satisfy that. And maybe all the other YVWs are like some tiny value. Actually, I think I meant to write here negative of 2 to the poly n, not 2 to the minus poly n. I meant to say some like super negative value. Remember, the objective is to, no, I should have written like, well, anyway, imagine it gave you back a bunch of like negative values for the y's. Well, it turns out that the giant negative values for the y's are not going to satisfy the moment constraints. And so imagine the ellipsoid did this to you. Ellipsoid algorithm did this to you, and then you came back and said, hey, just a moment, ellipsoid algorithm. I forgot to tell you one constraint in the k you should be solving. And it'll give back, imagine you tell the ellipsoid algorithm, I've actually got a separating hyperplane for you. It's the sum of all the y's should be greater than or equal to 0. I forgot to tell you that constraint, sorry. And it's actually legitimate for you, if you're trying to capture the moment constraints, to say that this is a valid constraint. What I'm trying to say is any YVWs that satisfy the moment constraints must satisfy this inequality. And the proof of that is quite simple. You see, this sum of all the YVWs, if there really are x's, real numbers x's that satisfy YVW equals XVXW, then the sum of all the YVWs is equal to the sum over V and W of XVXW, which by arithmetic is equal to the square of the sum of the XVs, and the square of a real number is non-negative. So this is sort of like a valid inequality for any solution y that satisfies the moment constraints. So you can, if the ellipsoid algorithm returns some y's that don't satisfy this inequality, you can just say, oh, sorry, ellipsoid algorithm, I forgot to mention you should also satisfy this constraint. Okay, and the ellipsoid algorithm will be like, oh, fine. So it'll like put that constraint in and like chop off like half of an ellipsoid, and like it'll keep going. Okay, we're using the fact here that the ellipsoid algorithm really only needs this separation oracle. And we're sort of trying to build a separation oracle for the set of all y's which satisfy this moment constraint. This is a bit tricky, so let me know if you have questions. Okay, so maybe you hand that off to the ellipsoid algorithm, and maybe now it comes back and it says, okay, I have a new solution for you. Y11 is 1 in my solution, and Y12 and Y21 are 100, and Y22 is 1, and dot, dot, dot. And you say, well, just a moment, ellipsoid algorithm. I forgot to tell you a constraint on the y's. I forgot to tell you this constraint. that y11 minus y12 minus y21 plus y22 should be non-negative. And that'll actually force the SDP, sorry, the ellipsoid algorithm to go back and revise its solution because, 1 minus 100 minus 100 plus 1 is not non-negative. Okay, and again, this is valid for any y's that satisfy the moment constraints. And here's the proof. If you have y's that satisfy the moment constraints, then this y11 minus y12, et cetera, is equal to x1 minus x1 x2 minus et cetera. And again, by a little bit of arithmetic, this is exactly the square of x1 minus x2, which of course is non-negative. So y's that satisfy this moment constraint will also satisfy this linear inequality on the y's. I'm getting a question. The question is, could you re-explain the moment constraint? So the moment constraint is, it's some kind of constraint on a collection of variables called yvw. You have one variable for each pair of vertices in the original graph. And the constraint on these collection of y's is that there should exist a collection of real numbers called xv, one for each x sub little v, one for each little v vertex in the graph, such that yvw is equal to xv times xw. Okay, so not all collections of y's are such that you can find x's that satisfy this. But some collection of y's have this property. It's kind of just hard to characterize them, but and I'll explain this a bit more later, but what we're trying to do is find some linear inequalities which are true of all collections of variables y which satisfy this property. It's pretty tricky, but that's what's going on. Okay, so maybe now you tell the ellipsoid algorithm, I had this separating hyperplane, so go back and find me a new solution. So ellipsoid will be like, all right, and it'll chop its ellipsoid with this half space, get a smaller ellipsoid, keep going. And maybe now it'll give you the same thing, but with y12 and y21 being negative 100. But then we're going to say, oh, I forgot to tell you, ellipsoid algorithm, here's another constraint that the y's, I forgot to tell you, are supposed to satisfy. And notice this new solution doesn't satisfy this new constraint. And it's a valid constraint again in the sense that any y satisfying moment satisfy this inequality because of, well, you can change these minuses to pluses. There's another question. I guess this moment constraint is quite confusing. The question is, are we quantifying twice over little v in the moment constraint? I don't think so. I don't think I've written anything wrongly. This means like, the moment constraint is that there exists a vector of x's, one real number for each vertex in the graph, such that for all pairs of vertices in the graph VW, yVW equals the product of xv and xw. Okay, so as a side note, I just explained to you why any y's that satisfy this very, I guess, hard to understand condition, it is a hard to understand condition, why y's that satisfy this hard to understand condition at least must satisfy these two inequalities. Also the inequality that their sum of all the y's is non-negative. That was the first one. And notice actually that this inequality here, since we also know that one of our constraints is that y12 equals y21, and another one of our constraints is that like y11 equals 1 and y22 equals 1, these imply that 2 minus 2 y12 is non-negative. Similarly here, and together these imply that y12 is at most 1 and at least minus 1. Okay, and that's nice. So I'm just observing here that, the equalities we have, that yvw equals ywv, that we can put into the linear program, and the equality that yvv equals 1, that we can put into the linear program, plus these inequalities, which are consequences of the moment inequality, enforce that all the variables y are between minus 1 and 1, which is a reasonable thing. That's something that should be true. Okay, but what's going on here? I mean, this is definitely a tricky thing I've been telling you about. So let me try to explain what's happening, or what I was doing with these examples where I was imagining running the ellipsoid algorithm and sort of implementing a separation oracle where I kept telling the ellipsoid algorithm, oh, I forgot to mention this inequality, and I forgot to mention this inequality, and so forth and so on. So one thing that was always happening is we would take some constants, some real constants, CV, and we would observe that for any real values x, if you sum up CV xv and square it, it's non-negative. That's a fact of life. Let me just expand that out. Oops, there's some sort of weird PowerPoint bug here. This should say C sub v, not v super c. Let me try to draw that here. Scribble this out. Okay, so if I expand this out, it means like just this is a fact of life about real numbers for any green C's. And therefore, if y's are numbers which satisfy the moment constraint, if y's are such that you can find reals x and x, xv, one for every vertex, such that this equation holds, then this constraint will also be satisfied by the y's. Okay, to repeat, any y's that satisfy the moment constraints must satisfy this green box constraint for every choice of real vectors C. And notice that these are linear inequalities in the y variables. So what I'm saying is any y's that satisfy the moment constraints must satisfy infinitely many different linear inequalities, all the ones that look like this, for some choice of real numbers C sub little b, one for each vertex. And this, what's called the SDP constraint, or what I'll call the SDP constraint, is to imagine adding all of these linear inequalities for all vectors of real numbers C. Now this is actually infinitely many inequalities that we're going to imagine including into a linear program. But remember I told you, like, the ellipsoid algorithm is so great, it can solve LPs even if you have like exponentially many or even infinitely many inequalities, as long as you can do this separation oracle. So I'll talk about this in more detail, but that's where this is going. So this SDP constraint is actually infinitely many constraints on the y's, linear inequality constraints, one for every choice of real vectors C, which are satisfied by any y's that satisfy the moment inequality, moment constraint. So this is what we're going to imagine doing. If you recall, we set up some kind of system that exactly captured max cut. It was some linear program involving these variables y. And it exactly captured it if you threw in these moment inequalities. In fact, let me go all the way back to that and just remind you of that. It's right here. So this is the LP, this part that's circled in white. It just involves the variables y. And we argued that if you could sort of solve this while enforcing this thing, which is the moment inequality, moment constraint, then you see, first of all, this fact, together with the moment constraints, would imply that these xv's have to all be plus or minus 1. And then, yv, will just be plus or minus 1, depending on whether xv and xw are the same or not. So xv, the x values now can be thought of as like a cut. Let's say all the plus 1 vertices are in the set S, and all the minus 1s are in the complement. Yvw is plus 1 if the edge vw is not cut, and it's minus 1 if it is cut. And then this expression is 1 if the set defined by x cuts the edge of VW and it's 0 otherwise. And so this sum represents the number of edges cut by the set indicated by x. So just as a reminder, this LP together with this moment constraint exactly captures max cuts. And what we found is that like this moment constraint implied like infinitely many inequalities, but linearly inequalities. And somehow we're going to try to add all these infinitely many inequalities to this LP and be like, oh, I have an LP now with like, you know, n squared variables and infinitely many inequalities, but I'm going to just try to solve it anyway. And hopefully this will do a good job of capturing the true thing that we were trying to encapsulate, this weird moment constraint. Okay. So let me go back to where we were. Okay, so again, we're going to try to enforce this moment constraint, which if we could exactly capture it, would give us max cut exactly captured, with this SDP constraint, where we're going to imagine taking our base LP and adding infinitely many constraints in our minds, one for every real vector of C, you get this constraint, and this constraint is implied by the moment constraints. So just to repeat, here are the key facts. The main key fact is that if like an algorithm imagines the original LP together with these infinitely many constraints, we can actually solve this LP efficiently. And the reason is we're going to actually be able to implement the associated separation oracle. I'll remind you what that means shortly, but that's what's going to happen. Second, remember these moment constraints imply the SDP constraints, but it's a fact that they're not equivalent. Okay, so what we've done here is made a relaxation. We had a program that exactly captured max cut, the original LP with the moment constraint. We relaxed it like the new LP, or the original LP with this SDP constraint, which is now an LP with infinitely many constraints, and we can solve it. So it's not going to exactly capture max cut, but just like we saw in the last lecture where you take an integer program, relax it to an LP, and hope it does like a reasonable job of capturing the problem, that's what's going to happen here. So a key fact is that this new thing that we can solve will give a good relaxation from max cut. Okay, and so for the remainder of the lecture, I want to explain this key point 1. Oops, how we can satisfy this efficiently. Oops, let me get on the right slide here. How we can solve this infinite LP efficiently. And in the next lecture, I'll tell you how you can use it, how you can like round the solution that it gives you to give you this excellent approximation algorithm for maximum cut, which always finds a cut that's within 87.8% of the best optimal cut.